All right, now we're at chapter 7, talking about chemical reactions. And if you remember that good old fashioned experiment where you make the volcano using the baking soda and vinegar, well, that is a specific type of reaction called a gas evolution reaction. And maybe for bonus points, you put in the red dye to make it even more visible. So other types of reactions, when you drive a car, the hydrocarbons react in a combustion reaction to form carbon dioxide, water, and energy, and then energy in the form of heat and or work. So that's a combustion reaction. There's other types of reactions like oxidation reactions, like when metals corrode, for instance. That's an oxidation reduction reaction. Other things, so laundry detergent with soap, because it has things that will soften hard water. Hard water is water that has a little bit higher concentration of magnesium and calcium ions, and the problem for that is that can create soap scum via a precipitation reaction. And soap scum, it's an insoluble stuff. So, and this can cause other problems, and it's usually just discoloration. And there is a way to get rid of it. So a lot of people just use plain old axle grease, but you can use other chemicals to get rid of it. So let's talk about evidence of chemical reaction. We talked about before, and remember, you cannot forget anything. Everything you learn is going to be come back to haunt you in this class. Chemical and physical properties. So physical properties are things that you observe without changing the substance, and chemical properties are things that you observe by changing the substance, and there's an exchange of atoms. So there's some easy ways to do this, and quite frankly, there are physical changes that correspond to chemical changes. So although it may seem kind of strange, but we will observe physical properties in part to prove chemical reactions have taken place. So for some things like this, and these observations, like I mentioned, are also physical properties. And here are a list of those there. And so here is a pictorial of this showing what has happened in a chemical reaction. So you see color change, formation of a solid that's used to be that in the normally dissolved two or more dissolved solutions, and that's known as a precipitation reaction. Gas evolution, just like in the vinegar and baking soda, emission of light, photons are emitted sometimes in reactions, and also emission absorption of heat, so exothermic or endothermic reactions. So this is not a chemical reaction. So just because one of those take place does not mean necessarily a chemical reaction has taken place, but boiling water to form steam, like, oh, it's a gas evolution reaction. Like, no, that's still a phase change. We're still H2O water, it's just H2O vapor instead of H2O solid. And this goes for many other things. So when steam condenses, it releases the latent heat, and that is a lot of energy. So, and that's a physical process. So just because energy is released or absorbed, that does not necessarily mean there's a chemical reaction either. So we chemists still need to be a little more observant and careful when we say something has reacted and has not reacted. So we've talked about this before, chemical equations. To the left are the reactants, to the right are the products. And then we've mentioned quite a bit about what the subscripts mean. For instance, here, methane reacting with oxygen to form carbon dioxide and water. So reactants on the left, products on the right. And then each of these, like CH4, means there's one carbon and 4 hydrogens. So let's take this a little further, and let's put states on each of the species. So parentheses, G is gas, L is liquid, and that's lowercase l. S is solid, and AQ means aqueous or aqueous. Depends on how you want to describe it in whatever accent you prefer. So if we look at this, let's add the states to all these, and this is all at the vapor phase. And because water quite frequently is a liquid, although in a combustion reaction, the water is typically water vapor. And let's look at this reaction here and look at the filled space model. There's the methane gas on the left reacting with oxygen to form carbon dioxide and water. And if you look at this, this is known as an unbalanced chemical reaction. So remember, matter is neither created nor destroyed. So from you can see here, we have we're missing hydrogen atoms and we have an extra oxygen atom. So well, there's something going on here. So when you balance a chemical equation, you have to make sure that each number, each type of atoms are the same on both sides of the equation. So in balancing this, and this equation is now balanced, you can see that the number and type of each atom are the same. There are 4 hydrogens on the left, 4 hydrogens on the right, 1 carbon on the left, 1 carbon on the right, and 4 oxygens on the left and 4 oxygens on the right. So this is a balanced chemical reaction. And this is the same as the previous slide, what I just said. So let's look at this. And what's important for balanced chemical reactions is it tells you ratios. If you remember in the previous chapter, we talked quite a bit about ratios. If you don't balance a chemical reaction properly, you will get the different ratios. And this is important because if you are trying to control a chemical reaction, having too much or too little of a reactant can cause a reaction to go too quickly, too slowly. It can also cause the wrong number of products. Not always do you want more products. Sometimes you want fewer products. It depends on which reaction you're going for. So this is the importance for knowing this. So how do you write a balanced chemical equation? Just write the chemical equation down, and then now you look for a strategy. It's easiest if there's only one compound on both sides of the equation, or an element. I'm sorry, if there's an element on both sides of the equation. In the way with with the combustion with methane, carbon is only found on both and one compound on both sides of the equation. So that's the easiest one to fix into place. And the next one, then you usually today it's easier to balance metals before nonmetals because metals tend to have less exotic bonding than nonmetals. Like you can see oxygen and hydrogen, especially hydrogen, is found in several different molecules. If it's a free element, balance it last. And if the coefficients contain fraction, change those to whole numbers. So remember, we use discrete mathematics in chemistry. The last step is to check to make sure that you have the right number of atoms on both sides of the equation. So let's try to balance this one here. So write the equation for the reaction of solid aluminum with aqueous sulfuric acid to form aqueous aluminum sulfate and hydrogen gas. So if you look at this, you can see aluminum is found on both sides of the equation. It's probably easiest to start there. So aluminum is on both sides, so let's start there. And also sulfur only appears, so we start with the metals first, so aluminum is there, and also sulfur is found both of these. And not for all equations. Well, it says aluminum and hydrogen both pure. You can go sides. It doesn't matter. I mean, the truth matters. You can do it any way you want. I said to look at the aluminum. I would have put a 2 in front of the aluminum already, but that's me. But then for the sulfuric acid H2SO4, the SO4, you can look at that as an entire unit. You can see it doesn't go on either side, so you're obviously going to need 3 of those. So put a 3 in front of the H2SO4. And the next one, you look at the aluminum. So put a 2 in front of the aluminum. So now the aluminums are balanced. And now you have to look at the hydrogens. So for the H2SO4s, you have 3 of them. 3 times 2 is 6. And then so there's 6 hydrogens on the left side, and look at the right side, H2 gas. Then you have to put a 3 in front of that. So now you have 2 aluminums, 6 hydrogens, 3 sulfate units on both sides of the equation. So from that, it's balanced. So yeah, I mean, I did it by looking at the sulfate units. Of course, if the polyatomic ions are not the same on both sides, then you have to be a little more exact on how you do this. So now we're going to move on to talk about solubility. So solubility means it dissolves. So if something dissolves in a solution, it dissolves. The solutions are typically clear, at least in chemistry class, but not all solutions are clear. So, like copper sulfate, for instance, that's soluble and it forms a blue solution. But in generally speaking, solutions are clear and tend to be not colored, but that's not true for all circumstances. If something is insoluble, it means it doesn't dissolve. So aqueous solutions are also homogeneous mixtures, meaning they are uniform across. And so let's here look at a sodium chloride solution. So it's an ionic solution, and the ions dissolve. So the idea is that the attraction between the water and the sodium ions and the chloride anions, both of these, the attraction of the water or whatever it's dissolving, the solvent, is more than the attraction between the sodium and chloride to form the crystal. So generally speaking, things are more soluble when they have small charges. So +1, -1. And also if they're really big atoms and or molecules. So when they're tiny and they're highly charged, they tend to be less soluble. So that's kind of beyond this class, but I just want to let you know some of the energetics involved. And when things dissolve completely, these are known as strong electrolytes. So it means that water can conduct electricity. So water, just pure water, does not conduct electricity very well. So water is a very, very, very weak conductor. And this may seem kind of weird because you're like, oh, well, what about all these stories I see about like people dropping things in the bathtub and being electrocuted? Well, there's a few things. First of all, if we're soaking in the bathtub, a lot of times we either sweat and we form our own slightly electrolyte solution, or we'll put things like bath salts in there, so like that kind of thing, or other ions, like as we're cleaning up, we have soap and that kind of thing in there. So also many times drinking water has things like chlorine in it, which is going to be increase the conductivity of the tap water. But pure water does not conduct electricity very well at all. It's considered a non-electrolyte. In fact, I was an expert witness for the state of Hawaii one time. There was a company that got an OSHA violation because they had electronic forklifts going around, and there was water on the floor. And OSHA cited them, and the company said, "Hey, water's a non-electrolyte, and this is fine." And I wrote back, "Well," so the state of Hawaii asked me if I would testify, and I said, "Hey, if it was like a laboratory, like a biohazard laboratory, everything is shut off, that's probably true. But if it's just like somewhere where it's like the ocean spray is around it, if there's other things around, if the floor is not perfectly clean, then it's going to conduct." So the other people withdrew their complaint after that. So score one for chemistry, I guess. But the time that you will see pure water not conducting electricity very well are things in like in a laboratory setting, where even in air, carbon dioxide will dissolve into the water, and it can slightly conduct then. Not so pure water is kind of at least here on Earth is kind of a misnomer, because rainwater, for instance, you'd think that's about as pure as you can get. It has a pH of about 5.67 is neutral, and that's because carbon dioxide absorbs. So be careful about the word pure, and we can find that in chemistry class. But when you put ions, put ions into a solution, it becomes electrolytes. And if you ever wonder what they say electrolytes in sports drinks, it just mostly means salt, usually sodium chloride. You can put other, maybe potassium salts in there too, but it's typically sodium salts. Another thing that's soluble, silver nitrate. Silver nitrate is a soluble solution. Be careful with this stuff; it'll turn your skin brown. So it is used. It's great for antibacterial action, but if you get the solution or the crystals on you, it will turn your skin brown. It'll stay for a while, and the effect is much more pronounced if you're fair skinned. So be careful with that. But so remember what I said about solubility. Nitrate, NO3 minus. So you have four atoms, all with one negative charge. That's a pretty large sphere of negative charge. It's a very loose sphere of negative charge. It's gonna be much easier to dissolve nitrates because of that very loose negative charge. So it's much easier to break apart the silver nitrate crystal than it is for a smaller atom, a smaller group, or a much more charged group. So, but silver and chlorine, chloride, and chloride it's only one atom. It's much smaller than the nitrate. So this, when the silver and the chloride get together, they can form a bond much more strongly than the attraction between the water, and it's much more strong than the nitrate anion. So because of that, it forms a solid, and this solid is known as a precipitate. So and this one here. So if be careful, this says it dissolves into independent ion. It does not dissolve into independent ions. It does not conduct electricity. Depending on what's in the solution, don't do a precipitation reaction like, oh, the solution is clean. It just means if you take silver chloride and throw it in water, it's not going to produce an electrolyte. So you can still have spectator ions and other stuff in a solution after you've gone and done the precipitation reaction. So be careful of that. This is a little misleading. But the compound silver chloride itself will not conduct electricity, at least in water, in a water solution. If you heat silver chloride up high enough, you can get it to conduct electricity, but it's going to be like 1,000 degrees Celsius or more before it'll conduct electricity. So here are the general rules. So ions that contain the following are pretty much always soluble. The alkali metals, ammonium ions, so these are big, small charged ions. Nitrate, acetate, big molecules. These are all, like I said, big atoms, big polyatomic ions with low charges. They don't really have that much attraction for anything. They're very happy to dissolve into water. The halides, chlorine, bromine, iodide. So these tend to be soluble too, and the word halogen even means salt forming. So, but there's a couple exceptions. So these tend to be soluble except for when they pair with silver, lead, or mercury. Same rule with sulfate. Sulfate tends to be soluble, with the exception of some of the alkaline earths, calcium, strontium, barium, and lead. So in lead plus 2 specifically, the compound is insoluble. Lead plus 4 actually will also be insoluble than lead plus 2. But this is also important for lead acid batteries for the lead plus 2. So keep on going. Now, these tend to be insoluble. So hydroxides and sulfides tend to be insoluble, with the exception of the alkalis and ammonium ions and sulfides. Calcium, strontium, barium sulfides tend to be soluble, and hydroxide pairs with calcium, strontium, and barium. The compound tends to be slightly soluble. I will agree with the textbook at this. They kind of consider it to be insoluble. It's not really soluble at all. Like calcium hydroxide, for instance, and some people consider it a strong base. You can drink calcium hydroxide saturated solution. It's not going to bother you. Whereas if you drink something like a saturated sodium hydroxide solution, you're going to be dead. So to me, that's kind of, I personally would consider calcium hydroxide to more or less be insoluble. But it can still be dangerous because if you take calcium hydroxide, sometimes called lime water, if you put that in your eyes, it'll really hurt. I've never put it in my eyes, so I don't know. That's why they get mad at people when they start putting their fingers, especially children, and you put children put fingers in the cement, partially because they have to redo the cement. The other thing is it's dangerous because if a kid does that and then rubs his or her eyes, it can cause some damage. So it's grainy and it's gonna react with the eye tissue. So that's that's a bit more. That's gonna be a tough day for the child and the people looking after the child as well. So, anyways, moving on. Carbonate and phosphate. These tend to be insoluble, with the exception of the alkalis and ammonium ions. And see, if you're wondering the general rule, and I told you the general rule, very big very big charges and smaller ions tend to be insoluble, and small charged and big tend to be soluble. So that's a more general rule from that. And then the reason for that is the Coulombic force. So but moving on, here's a picture of showing what I described before, so you can look at this and use this logic flow if you prefer the pictorial to the chart. And again, here's the insoluble chart. So let's go to precipitation reactions. So look at potassium iodide reacting with lead nitrate, both in solution. You pour them together and it forms this really pretty yellow lead iodide solution. So from that, and also you get potassium nitrate still in solution though. And it has a real pretty yellow precipitate. I don't tend to do this as much because the lead is toxic and it's also it's hazardous waste. So if you want to do a precipitation reaction at home, soap scum is one, so you can use bar soap and hard water. You can also go to the store and you can buy TSP, trisodium phosphate, put that in solution. You can mix it with Epsom salts, magnesium sulfate, and it'll make a magnesium phosphate precipitate. So and that's white. So it's not going to be as pretty as the lead iodide, but if you wanted to do a precipitation reaction at home, that's one you could do. Okay, so precipitation reactions, and this is a chemical reaction because a new compound is formed that's no longer soluble. So we have to take two solutions that contain soluble compounds, combine them, and maybe they will form an insoluble precipitate. So from the previous example, we have this, and it forms, you have these two solutions that are just fine sitting together, sitting on their own, but when you mix them, the lead and the iodide come together and it forms a precipitate. So actually the arrow is in the wrong part. The old school was to have the arrow going down. Arrow going up means gas evolution, so this is a mistake in the slide. So we have to look to see which is insoluble. Is potassium nitrate going to be insoluble, or is lead iodide going to be insoluble? We have to look at both of these, and then we have to look at the rules. So all alkalis are soluble, all nitrates are soluble, so you know that potassium nitrate is not going to form a precipitate in this circumstance, but lead iodide, halogens tend to be soluble with the exception of lead plus 2, and because of lead plus 2, it's going to precipitate down. So then you get lead iodide on the bottom, and it's down. This is called a precipitate. Sometimes you form compounds that float on the surface of the water. Those are known as supplicants, but precipitates go down, and they tend, and ionic compounds, generally speaking, tend to sink. So you'll hear precipitation reaction used much more frequently. And notice the states of the equation. Potassium iodide and lead nitrate are aqueous. The lead iodide is a solid, and the potassium nitrate, that's aqueous. So the potassium ions and the nitrate ions just kind of float around and do nothing, though. So we'll learn about those later. We call them spectator ions. But the lead and the iodide are the only ones doing anything. So they're the ones that are actually doing the work in this. So we'll talk about this in a little bit. So what about when no reactions occur? So if you look here, we have potassium iodide and sodium chloride. So two alkalis, two halides, and the halides corresponding ions are not exceptions. And you look at this one, there's absolutely no reaction. You like to say, oh, I learned about this in chemistry class. What if I mix these two solutions? What's going to happen? And like, the answer is nothing. Nothing has happened. And that means you have not formed a new compound. There has been no chemical change. And now you have to do something else. You did not see a interesting chemical reaction for this. There was no reaction. So what about another one? So you have to, predicting them. So if you look at these reactions here, so sodium carbonate, this is aqueous, and copper chloride, also aqueous. Now you have to look at the rules and figure out, like, okay, is the copper carbonate going to be insoluble, or is it going to be soluble? Is the sodium chloride going to be soluble or insoluble? Like, for me, the general rules here: the copper is +2, carbonate's -2. That's gonna, without even looking at the chart, although I do have the chart memorized, I know that's not going to be soluble. That's definitely going to be stronger than the attraction between water. And sodium chloride, we already know it's soluble. So we have to look at this, and we have to look at the other products. So like the sodium chloride, but you should probably already know sodium chloride is soluble. Sodium salt is pretty soluble in water. If you've ever tried to get a concentrated brine solution, you put a lot of salt into water. It's about 25% by mass, and I remember making brine solutions. I'm like, man, this is taking forever, kind of thing. I'm like, oh, I think I'm done. Then I put the stir bar in and I let it stir for a while, and I come back 5 minutes later, it's all dissolved. I'm like, come on, dissolve. So, but anyways, sodium chloride is very, very soluble in water. As before mentioned, copper carbonate is insoluble. So, copper is not an exception to the carbonate being generally insoluble. So if all the products are soluble, you write no reaction. And if there is a product that is going to be insoluble, write it and indicate the S for solid for the insoluble product. And at the end, balance the equation. And looking at this, it's pretty well balanced, except you need a 2 on the sodium chloride because there's 2 sodiums and sodium carbonate, and you're going to generate an extra one, and also on the copper chloride. So you have to have the 2 on that. So let's move on and talk about different types of equations. Molecular equations are showing the neutral formulas for every compound and chemical reaction. So this equation here, silver nitrate plus sodium chloride forms silver chloride plus sodium nitrate. So in my mind, I'm picturing this. I go into the lab, I grab a jar of silver nitrate and a jar of sodium chloride and 2 beakers of water, and then I take some silver nitrate out, I put it into 1 beaker with the water, I take some sodium chloride out and put in another beaker of water, and I stir these together and I stop. Now this is the beginning. I have a solution of silver nitrate in water, a solution of sodium chloride in water, and now I take the beakers and I pour them together, and now they react, and then the silver chloride precipitates out on the bottom, and then there's this solution on top. But the solution on top contains sodium nitrate. So this is the molecular equation. So it tells you the states and where things start off with. Now let's do the complete ionic equation. The complete ionic equation, we're going to take all the species and break them apart into the different ions. So the silver nitrate becomes silver ion, aqueous, nitrate, anion, also aqueous, silver ion, aqueous, plus chloride, anion, aqueous. And this yields silver chloride solid, but still on the product side are sodium ion aqueous and nitrate anion aqueous. So now we did not have them in molecules. We just put all of the ions, all of a sudden they're doing everything. But you might notice that the sodium and the nitrate, they are not participating in the chemical reaction. I guess I didn't miss this point. Do not separate solid, liquid, or gaseous compounds. Only the ionic compounds. So the one because they're aqueous, because they're floating around the nitrate and the sodium and the chlorine and the silver all on the left are floating around independently. They're not joined together for any appreciable amount. So do not separate out the ionic compounds, but do not separate out any solid, liquid, or gaseous compounds. So aforementioned sodium and nitrate, these are both spectator ions. So that means that they're sitting there and they're not participating in them. It's kind of like when you're in a sporting event. If you're a spectator, you are not actually on the court, on the field, doing the work. You are observing, and it's kind of like they're just kind of observing. So we can do the complete ionic equation where we take away the spectator ions. And this is like the Cliffs notes or the spark notes of the chemical reaction. This is like the abbreviated story. Remember I told you that long story where I took silver nitrate and sodium chloride and I made 2 beakers and I dissolved the solutions and I poured the solutions together and then a precipitate formed and I determined the precipitate was silver chloride, and there are still sodium and nitrate anions floating around in solution. That is the long novel version. That is the complete ionic equation or the molecular equation. This is the so what. This is the Cliff Notes, silver and chloride in solution, meet, form, solid, and I'm done. Right? So this is the quick and easy chemical reaction. So that is the net ionic equation. So it is the very short story of the long chemical process. So to summarize, molecular equation shows the neutral formulas, also in the states, right? So aqueous for this states. Complete ionic equation separates out all the species that are present in a solution. And the net ionic equation just tells you what happens. These are the ones that react, done, end of story. So we're going to talk about different types of chemical reaction. We talked about precipitation reactions. Let's talk about acid-base reactions. So here, hydrochloric acid plus sodium hydroxide makes water and a salt. So this is true for acid-base reactions, generally speaking, for a specific type of acid-base reactions. And this is where most of them that matter. We can argue fine points about acid-base reactions in other courses. But for this course, you can consider this to be true. But so some things about acids. Acids tend to taste sour. Well, I shouldn't say tend to. They always taste sour. They turn litmus red. They cause cells to shrink. Most metals form hydrogen in the presence of acids. Bases tend to taste bitter. They make biological cells expand. They add negative charge. Acids add positive charge. They turn litmus blue. And then, but now those are properties of acids and bases. And when they react, they form a salt. And salts no longer have the properties of the acids and bases. So sodium chloride salt does not turn litmus red or blue. It does not taste sour or bitter. It does not make hydrogen gas in the presence of metals. So salt is something new. It is a new chemical that does not have the properties of the acid or the base. So that's the idea. That's the proof then of the chemical reaction there. That, and you also generate water. Although I know they're both aqueous, but you generate more water. So more water is created. And these are also called neutralization reactions because it no longer has its the solutions, the reactants no longer behave like acids or bases. So, and I didn't mention this about bases. Bases feel slippery. This is not true for everything though. So sulfuric acid also feels slippery. Oil, many hydrocarbons, these feel slippery. Hydrocarbons are not acidic or basic. They don't have this property to them. Only water solutions have this. And sulfuric acid obviously is an acid that's slippery. So this is a general rule, but it's not true for all things. So I think the logic, and the reason is why do bases feel slippery? It has to do with the fact that they add negative electron charge, and for biological creatures, generally speaking, surfaces are negatively charged because cell membranes are phospholipid bilayers, and the surface of that is going to be a negative charge. And adding negative charge causes the charge to expand. And that just makes things, and the so what was that? It makes things feel slippery. So that's how the whole general thing. But then again, this is not a general rule that all things that make things slippery are bases. Bases tend to make biological surfaces slippery, but they don't necessarily, just because something is slippery does not mean that it is a base. So keep that in mind. But if you do take soap, soap feels slippery, and soap is alkaline, it's basic. So here's some common acids and bases. Hydrochloric acid, also known as muriatic acid, that is an acid that we use in our stomachs. So we humans and many other animals use this to aid in digestion. Hydrobromic, honestly, it's not that common. Neither is nitric, although we use it quite a bit in industrial processes. It's hard to get because it can used to make explosives. We do make quite a bit of sulfuric acid. This is also known as battery acid. Perchloric acid is also not as common because it can be used to make explosives, just like nitric acid. Acetic acid is extremely common. This is what's in vinegar. Sodium hydroxide, this is also known as lye, L-Y-E, lye. So it is found in various things. You can find it in certain drain cleaners, for instance. Lithium hydroxide, I also don't think this is terribly common. You can find it in the chemistry lab quite a bit. Same with potassium hydroxide, although you can use potassium hydroxide to make things like liquid soaps. Calcium hydroxide, it's moderately found. It's you can take lime and you mix it with water, and you form, that'll form lime water, which is calcium hydroxide. I guess it depends on how you mean by common. And also lime, if you ever heard the limelight, when you take lime, calcium oxide, and you heat it up, it glows. So that's when you say addicted to the limelight. That's the old school way to generate light. Barium hydroxide, this is not a common one. It's commonly used in chemistry, but this stuff, it's alkaline and it's toxic. It's not a fun one to play with. Of this list here, I would probably say hydrochloric and acetic are actually very common. As far as the bases of the ones there, I'd say sodium hydroxide is common because you can find and purchase lye with that. But the rest of them, you're probably not going to come in contact with them in your day-to-day life as much. Actually, maybe sulfuric acid, because many car batteries have that in there. But be very careful if you play with a car battery. In fact, do not play with a car battery. So let's do an acid-base reaction. You must recognize these reactants as an acid and a base. So, and a lot of it's in the name, right? So, nitric acid and calcium hydroxide. We're going to talk about acids and bases in a future chapter in much, much more detail. So, and this arrow is pointing up. It should be pointing to the right. It is a typo with this. So we look at this and then we balance the equation. So how do we balance the equation? So looking at calcium hydroxide, there's calcium on both sides of the equation. But you look at the nitrates, there's 1 on the left and 2 on the right. So you need to have a 2 in front of that. And also the hydroxides are going away and we're losing 2 hydrogens, so you form 2 waters. So that's how you balance the equation there. So we've talked about acids and bases. We will talk about acids and bases much more in depth later because we use acid bases quite a bit. But let's talk a little bit about gas evolution reactions here. So, and just like precipitation reactions where a solid is formed, we're going to have a reaction where a gas is formed. So sulfuric acid plus lithium sulfide is going to form hydrogen sulfide gas and lithium sulfate still in solution. And of course, when you mix these two solutions together, bubbles form. And it's going to be very stinky bubbles with hydrogen sulfide because this stuff smells absolutely terrible. More common one is so hydrochloric acid with sodium bicarbonate, baking soda forms hydrogen carbonate and sodium chloride, and then that's an intermediate step. But then it forms liquid water, carbon dioxide gas, and sodium chloride. But you can even skip the intermediate step if you want, and just go right into the carbon dioxide. So the hydrogen carbonate or carbonic acid there. That is that is known as an intermediate. So it's sort of like someone who's dating and then gets married. The intermediate state is an engagement, and that intermediate state can be very very short. So some intermediates can last a while, but generally speaking, intermediate states don't stick around for very long. So here are some types of gas evolution reactions and also their intermediate products. So carbonates, or hydrogen carbonate can form carbon dioxide. Hydrogen sulfite can form sulfur dioxide, and ammonium hydroxide can form ammonia. Although quite frequently we use NH4OH aqueous and NH3 aqueous. We can use those interchangeably. You'll see that quite a bit in chemistry classrooms and labs. And part of that is because ammonia is an alkaline solution. So usually putting the OH in there tells you that that's an alkaline solution. So, and ammonia, man, that stuff will knock your lab glasses off when you smell that in the chem lab. Because you jerk your head. I mean, it's a smelly stuff. Well, it doesn't smell too bad. It's just really strongly smelling. So here are some examples of gas evolution reaction. You can see that quite frequently they are, in fact, usually acids. There's a few more. I mean, these are not the only ones. So a scary one is like a cyanide salt plus acid will form a cyanide gas. So, and I've smelled cyanide gas. It smells really good. It smells like roasted almonds. But of course, it can be very dangerous. But anyways, here are some examples of those. And then ammonium chloride with potassium hydroxide to make, the bottom one, to make liquid water, ammonia gas, and then potassium chloride. So when you write these, you have to recognize that the chemical reaction happens, and also that the intermediate step then can decompose into something. So with this, though, at least for me, if you were my student, I typically have my test be open book, so you can just look to the chart for here. And for many cases, the gas evolution reactions are not as common that you see in other ones. If I say that they're not common, of course you can, pour acid on limestone and it forms carbon dioxide. That's very common. But I mean, like the number of these reactions, there's many more acid-base reactions. There's many more precipitation reactions that you'll see before you'll see gas evolution reaction. But anyways, moving on, you have to recognize seeing what the intermediate step is here and what it decomposes to. To be honest with you, I don't necessarily even think about the intermediate steps. I just kind of look at the end products and think of them that way, because the intermediates are so short-lived. I don't even think about that. So it's however you want to figure it out. So then when you write the equation, and like I said, you don't have to put the intermediate step in there, but then write out the equation. So like nitric acid plus potassium sulfite, and then that forms the intermediates, and then forms water, sulfur dioxide gas, and potassium nitrate, and then finally balance the equations. So let's see here, on both sides of the equation, there's going to be two potassiums, so you're going to have two potassiums at the end, and those two potassiums are going to, you need two nitrates, and then you need two nitric acids, and then There's an extra. Oh, the extra oxygen goes in the water. Okay, then you are balanced. So I was balancing it in my head and verbalizing my thoughts at the same time. So if you wondered how I did it. Okay, so what? Why do we care? I told you our stomachs have hydrochloric acid in them, and sometimes you can get too much, and you can get a sour stomach, and or you can have the acid leave your stomach back through the sphincter between your stomach and your esophagus, and that can cause a very unpleasant feeling called heartburn. So you can use antacids to neutralize stomach acid. And the most common ones we use are calcium chloride and magnesium hydroxide. So I'm sorry, calcium carbonate. Excuse me. Calcium carbonate and magnesium hydroxide are the much more commonly used ones. We don't tend to use aluminum hydroxide or sodium bicarbonate anymore. But that's the acid-base neutralization reaction. And even though this is listed, these are not all antacid. The Pepto-Bismol there is not an antacid. That is bismuth subsilicate. That is not an antacid, so it shouldn't be up there. So we're going to move on and talk about oxidation and reduction reactions. So sometimes just abbreviated to redox. So just sort of reduction, oxidation. Well, the reason is because they always come in together. Because oxidation is the loss of electrons and reduction is the gain of electrons. And so whenever electrons are lost, electrons are gained, or whenever electrons are gained, electrons are lost. So these reactions always happen together. So that's why we combine them together into one. And here's an example of one. Anything that involves electron transfer. And things like batteries work by electron transfer, bleaching of hair, these type of things are all going to be oxidation reduction reactions. So what's going to take place? Well, in an oxidation reaction, electrons are lost, and reduction is the gain of electrons. And if you need help remembering that, oil rig, oxidation is loss, reduction is gain, or Leo Gur, like lions say gur, Leo Gur, lose electrons, oxidation, gain electrons, reduction, whatever. Well, however you want to remember it, if those help, maybe it helps you. So let's have this reaction here. Two sodium atoms react with a chlorine gas to form sodium chloride. So we haven't gone over oxidation reduction, the oxidation states, but a free element is said to have a zero oxidation state, and an ion is said to have the charge of the ion. So sodium has a zero oxidation state, chlorine has a zero oxidation state, and in this case, the sodium atom gives an electron to form a sodium ion. So sodium metal going to sodium ion generates an electron, 2 electrons plus chlorine gas. These absorb 2 electrons and then become 2 chlorides. So chlorine is gaining electrons. Sodium is losing electrons. Chlorine is gaining electrons. Therefore, this is an oxidation reduction reaction. And redox reactions are the following. When something reacts with elemental oxygen. So if you haven't guessed, what is the most common oxidizer, the thing that oxidizes things? What could the most common oxidizer be? Oxidizer. Gee, does that sound like oxygen? So yes, oxygen is a very, very common oxidizer, especially here on Earth, where 20% of our atmosphere is oxygen. So when a metal reacts with a non-metal, this, generally speaking, means that the metal is the reducing agent. It gives its electrons away. So, and pretty much very commonly, one substance transfers electron density to the other substance. So combustion reactions. So fire is an example of a combustion reaction. If you ever wondered what is the definition of fire, fire is a rapid oxidation reduction reaction. So you didn't come to chemistry class today expecting to learn the definition of fire. Well, you've just learned the definition of fire. Fire is a rapid oxidation reduction reaction. And combustion reactions, these are commonly done here on Earth. And oxygen reacts with one or more compounds to form water and very commonly carbon dioxide. So combustion reactions are exothermic, which means they emit energy and or heat. So and compounds that have carbon and hydrogen or oxygen, they form carbon dioxide and water. So other combustion reactions, you can burn metals, for instance. So magnesium burns very brightly, and that forms magnesium oxide, for instance. So you can do it. You can form other things. So let's write the balanced equation for the combustion of methanol and oxygen. So we have methanol reacting with oxygen to form carbon dioxide and water. So this is going to be a little more complicated though, because we are going to have an extra oxygen. For what I do is I tend to let fractions happen when I do this. So and let me balance this without the whole number. So methanol on the left has one carbon. Carbon dioxide has one carbon on the right. So I'm going to go ahead and give it a 1-to-1 ratio and set that ratio. Now I'm going to have 4 hydrogens in the methanol and 2 in the water on the right. So I'm going to put a 2 in front of the water. So now I have I have 2 oxygens on the left and 3 oxygens on the right. So how am I going to do this? I'm going to write 3/2 oxygen. So now, because of this, of course, balancing with the fractions, I have 3/2 oxygen. I'm going to multiply the whole thing by 2 and then get the equation as written there on the bottom. So that's the way that I would balance this. And I would kind of have an intermediate fraction and then at the end bring it up to whole numbers. Quite frequently, you will see sometimes things listed as, say, 3/2 oxygen. And the reason for that is for like keeping track of species. Like if you're a chemical engineer and you're doing cells on an Excel document and you need to program reactants and products, you can do it in a fractional way to keep your math easier when you program your either your program, or for me it's usually an Excel sheet. So if you're wondering why you would not do the proper thing, it has to do with making the math more simple. So, but strictly dealing with chemistry, we deal with discrete numbers. So here is a pictorial to show the different types of chemical reactions. And when you have rapid oxidation reduction reactions, you can have a combustion reaction. And classifying what they do, so we're going to talk about chemical reactions in general. We can have a synthesis or combination reaction. So 2 things come together to form something new. So lead and chlorine come together to form lead chloride. Decomposition goes the other way. Ammonium carbonate react to form ammonia vapor and carbon dioxide and water. So that is a decomposition reaction. So a single reactant forms products, and it can be more than 2. Single displacement, where you take one and one bumps the other one out, and then double displacement, where 2 things react and they exchange, do the complete exchange with each other. So those are the general chemical reaction types. And so here are some synthesis reaction. You make new things. So sodium plus chlorine makes sodium chloride solid. We've combined those together. and a decomposition reaction. So I guess here's another one. I gave you my own before I thought to move on. You can decompose water into oxygen and hydrogen. So using electrolysis. So single replacement, here you can take zinc metal, throw it in a copper chloride solution, and then copper metal will form on the surface of the anode, and then the zinc will go into solution. And a double replacement, so this is, I don't know, I guess I called this a combination reaction. I could see the thing is that they don't form I guess, well, you'd have to dry it to form the new compound. So that's the double replacement reaction. You have potassium iodide and lead nitrate forms two new substances. I guess you could say that, sure. So classification flow chart here. And here is the review, the chemical reaction. So we went over the evidence for chemical reactions. Talked about the different types of solutions. That's different. So talk about solubility rules, insoluble rules, different types of reactions, precipitation, acid-base, gas evolution, oxidation reduction, and a subset of that, combustion reactions, and the different types of reactions. Here are the learning objectives and the copyright statement. Thank you for listening.